Okay, there's some surprises and some things I want you to see as we create sign tables or we evaluate sign tables to make a graph from. And they happen particularly when we have some strange functions with odd powers on them, or if we have rational functions as fractional functions. So to create this sign table, remember the first thing we're going to do is consider intercepts. And so I'm thinking of a y-intercept here. And for a y-intercept, I let x be 0. And so if x is 0 in this function, then the y value is just 0 plus 0 to a power, so the y value is 0. So that was very quickly done. In the case of an x-intercept, as we know, that might be more difficult. But what we know there is with an x-intercept, the y value is 0. And so we're ending up solving the equation 0 is equal to x plus x to the power 2/3. Now to solve that equation, here's what I would do. I would say, okay, I have an x in both of these positions, and so I'm going to factor out an x, and that would leave me a 1 plus, x to the negative 1/3 power. Okay, whoops, negative 1/3 power. And so then I would set each of these factors to 0. I'd get x equal 0. And then I'd set, that's the first factor, and then I'd set 1 plus x to the power negative 1/3 equals 0. And of course, x equals 0 already tells me that one of my x-intercepts has an x value of 0 and a y value of 0. So I actually have two x-intercepts, don't I? Now, the second x-intercept still has a y of 0. We just don't know the x value yet. And we're going to get it from this equation. And so I'm going to subtract 1 on both sides. And so I get x to the negative 1/3 power is equal to negative 1. And then it probably is useful to me to write x to the negative 1/3 power as 1 over the cube root of x. So I have that being equal to negative 1. Of course, the only way that can happen is if x itself is a negative 1, because I need 1 over negative 1. So I conclude x is negative 1, and so there's my other x-intercept. Okay, now I'm worried about all of the critical numbers. Okay, all of the critical numbers, that is, critical numbers of the first derivative and of the second derivative. And so I need f prime of x, and when I look at this function, when I take the derivative, I get 1 plus 2/3 times x to the power negative 1/3. Okay, well, that's familiar looking, isn't it? And then, of course, the second derivative, I take the derivative of that, and of course, derivative 1 is just 0, and so I end up getting, well, negative 1/3 times 2/3 is negative 2/9. And then I'd reduce the power on a negative 1/3 by 1. That'll give me a power of negative 4/3. Okay. Now what I'm ready to do is find the critical numbers based on these two things. And one of the issues, well, of course, what I want to know here, one case is where is this first derivative equal to 0 and where is it undefined? Now, it may be useful in this case to write this a little differently. So let me separate these so I don't get them to running into each other. This is actually 1 plus 2 divided by 3 to the 3 times the cube root of x. See, x to the negative 1/3 is nothing more than 1 over x to the positive 1/3, which is 1 over cube root of x. So that form helps me decide that clearly this function is undefined when x is equal to 0. Now, the next question would be, is there any value of x for which this thing is equal to 0? And then that would be what we are working on right here on the left side. That would be 1 plus 2 over 3 cube root of x is equal to 0. And we want to know if that has a solution. So I'd what I would do is I'd multiply both sides of this equation by that denominator. So when I multiply the 1, I get 3 times cube root of x. And then when I multiply the fraction, I get 2. And then when I multiply 0, I get 0. And so now it looks a little better, and I just have a regular equation with a radical in it. So what I do is I get the 2 and I isolate the radical. So I would subtract 2 on both sides, bring this on down, and then I divide on both sides by 3. And now I have the radical isolated, and so I would cube the radical so that I could get rid of it, but then I'd have to cube the other side as well. So I cube both sides, and that leaves me with x is equal to negative 8 over 27. Now, over here when we're looking at the set, so far we have a critical number of negative 8 over 27 and a critical number of 0. Now, the critical numbers of the second derivative, okay, come from what we see over here. And so what we could do is write this derivative, let's go ahead and write it a little differently so that we can deal with it. This is actually negative 2 divided by 9. Let's see, we have a cube root of x to the 4th power, don't we? That's what we really have there. And we could simplify that further, but when we look at that fraction, then we see that it's undefined. It's undefined when x is equal to 0. Now, that happens to be a critical number that we have already for the fact that it was a critical number of the first derivative. Now, one thing that we can look at also here is that when we look at this derivative, it's never equal to 0. See, that can never happen because we don't have any x values in the numerator. The only x's we would put in would be in the denominator, and so we'd never get a 0 fraction because we'd have to have a 0 in the numerator. So there's only one critical number for that. So that kind of, when we're getting ready to set up our sign table, we really only have 2 different critical numbers. One critical number is shared by the first and second derivative, and the other critical number is just with the second derivative, first derivative. And so the critical numbers are these 2 values, okay? So our intervals are going to be negative infinity to the number negative 8 over 27. And then there'll be negative 8 over 27 interval to 0. And then there'll be an interval from 0 to infinity. So this kind of sets up how many rows we're going to need. We're going to need a row for the first interval here, and we're going to need a row for this critical number, and then a row for the second interval, and a row for this, and then a row for this last interval. So we need a total of 5 rows in our table, don't we? Okay. And so now let me draw the table so that we can get ready to fill in the table, and then we'll use that to make a graph of the function. Okay, I've got my table kind of set up, ready to draw. Remember, the first interval furthest to the left was negative infinity to negative 8/27. And then we had the critical number that was negative 8/27. And then we had the interval from negative 8/27 to 0. And then we had the critical number, 0. And then we had the interval, I've got some stray marks there, don't I? From 0, ignore that mark there, to infinity. Okay, and then we come down here and let's see, our first derivative had critical numbers at what? Negative 8/27. So our first derivative, oh yeah, we had a critical number where it was 0, didn't we? At negative 8/27. Now that our other critical number for the first derivative was where the first derivative was undefined. It wasn't 0, it was undefined. So remember, at the derivative here, the first derivative was undefined. Okay? So we can't put a 0 there. So that's something that's different than we've seen before. Now, in our second derivative, it had a critical number of 0, but that was also where the second derivative was undefined. It wasn't 0 there, it was undefined when x was 0. And so we have an undefined position there as well. Now, it so happens that we found out, kind of by happenstance, that when x is equal to 0, y is also 0, so we could fill this in with a 0. That's actually going to be a point on the graph, isn't it? And what we haven't done is calculated f of x when x is negative 8 over 27. And that takes a bit of work, but I'm going to tell you what we get there. We get 4 over 27. And I'm convinced that you can do that. It's just going to take a little bit of work. And I wouldn't mind you using a graphing calculator, not a graphing calculator, pardon me, a scientific calculator, but we certainly don't want to be using a graphing calculator to do this work because we're trying to find what the graph looks like without the aid of a graphing calculator. Okay, now let's go a little further here. Now, in the case, what do we need to do next is we need to fill in the first derivative and second derivative columns with pluses and minuses, don't we? And I'm not going to go through, I want to tell you enough things and get to the graph of this, but I'm convinced that you could choose an x value in this first interval from negative infinity to negative 8 over 27. For instance, something as simple as negative 1. Okay, and we could plug it into the first derivative, and when we did, we would find out that we actually got a positive value. Okay, so we would get a plus value there. Now, while I'm working on the first derivative, then I would look at the interval from negative 8 over 27 to 0. And now this would be more difficult, granted. And we'd have to find some number in that interval, and then we would have to use that value in the first derivative. For instance, maybe negative 1 over 27. See, that would be in that interval, wouldn't it? And anyway, we would use that idea, we would use that interval, and in that case, we'd actually find that the first derivative, that number, the first derivative is actually negative. So we'd have a negative sign there. And then we'd check on the interval from 0 to infinity. And of course, there's lots of things we could use there. We could use an x equal 1 or x equal 8 or 10 or 100 or 1,000,000. But when we do check something there, then we'd find out that the first derivative was positive. Okay? And then we're going to go through and do the same thing for the second derivative. So what's going to happen, I'm going to choose a value in this first interval, negative infinity to negative 8 over 27, and check it into the second derivative, and I'm going to find out that it's positive here. Now, that one piece tells me that it's positive in all of these other boxes up to the undefined, because remember, we only have one critical number for the second derivative, and so we can't change the signs until we get past a critical number. And we don't know that the sign's going to change, but we can't change. So those first three boxes all have to be pluses. Now, we go in and we check in the interval from 0 to infinity, the second derivative, like we could use a 1. And if we did, we would find out, oh, and I'm wrong. Okay, I'm sorry. I really apologize for this. Okay, actually what I found out was I got a negative and a negative and a negative. Okay, and it has to be the same all the way through. And then when I go and check in the second derivative in this last interval, I also get negative. So I apologize that I've really blown that. I wanted it to be nice and neat for you, but that's the way the sign table would look, but of course unscratched out. So we begin to start filling in the conclusions, and you see in this very first row that we're increasing, okay, and we're concave down. Increasing and concave down. So that's kind of telling us it looks like that, doesn't it? Then in this next row, we have a critical number of the first derivative. And we notice that the first derivative in that column is going from a plus to a minus as we go past that zero. So we do have a maximum or a minimum. And in fact, we're increasing and then decreasing, so we actually have a relative maximum, don't we? And we know the relative maximum is this point, negative 8 over 27 for the x value and 4 over 27 for the y value. Okay? Now, next thing that we have is the interval negative 8 over 27 to 0, and we see the first derivative is negative, so we're decreasing. And the second derivative is negative, so we're concave down. Okay, concave down. And then we get to where x is equal to 0, and we actually have two critical numbers. Okay, but they're from undefined values, but they're critical numbers. I mean, x equals 0 is a critical number for both the first and second derivative. Now, in the case of the first derivative, look what's going on. We're changing signs, negative to positive. And so if we change signs from negative to positive, that means we were going down and going up, so we actually have a relative minimum, don't we? Now, and that relative minimum is 0, 0. Now, the other issue here is that when we look at the possibility of this undefined second derivative, that's a critical number, we could have, at a critical number of the second derivative, an inflection point. But to have an inflection point, we have to change signs of the second derivative, and it does not change signs. So this is just kind of a note. There is no inflection point. Okay, and then we look at the very last row, and we see that we have a plus for the f prime, so that means we're increasing. Okay, and we have a minus for the second derivative, f double prime, and so that means we're concave down. So this sucker's concave down all of the time. Now, that's kind of strange. Let's kind of look at, remember in this first row, we kind of got that idea. Then we had the relative maximum, and it was decreasing and concave down, and it's kind of that idea. And then we had a relative minimum, but no inflection point. So it didn't change concavity, it doesn't change concavities. And then lastly, it's increasing and concave down. Now that's kind of a strange look. But if we kind of put those pieces together from top to bottom, left to right, then what this is going to look like, we kind of get an idea of what this is going to look like. That's the first part. And then the second part's doing like this. That's the second part. And then the third part's doing like that. Ah, okay. Yes, see, it's concave down everywhere. And we actually have a relative maximum and a relative minimum. Now, we need to be a little more careful when we do this, but now we have an idea of what it looks like. Now, right here, I need to say one more thing, because in your homework, you're going to need to be able to fill in a sign table. But it's not, it'll accept pluses, and it'll accept minuses, and it'll accept numbers. But it will not know about how to deal with increasing or concave down, how you won't write those out. So it will give you these directions, so you need to read the directions. But when you have the situation that is increasing, you need to put the little symbol that almost looks like an arrow pointing up, doesn't it? It's not an arrow, it's just that housetop looking thing, okay? And there'll be that button on the left side that will allow you to enter that. And then you would put a comma, okay? And for concave down, you put like a intersection symbol, like an upside down U. So you would enter for increasing and concave down in that fashion. And on down here, if you were doing decreasing, well, you would put what looks like a V. Now these tools are available in that left side toolbox. And then you would put a comma And for concave down, you'd still put the upside down like this. Now, so what's going to happen, increasing is going to look like this. In place of increasing, you're going to put this. And in place of decreasing, you're going to enter the symbol that is this way. And in the place of concave down, in your homework on the computer in my math lab, what you're going to end up putting is concave down, you're going to put that symbol, which, again, these are available in that toolbox. And for concave up, then you're going to put this symbol. Okay, so we get the ideas there. And then when we have relative maximums or relative minimums, if you have a relative maximum, then you're told to enter MAX, okay, if you have a relative maximum. And if you have a relative minimum, you're told to enter MIN, okay? I don't think it matters whether it's uppercase or lowercase. And if you have an inflection point, you're told to enter IP. Okay, so, and you won't need to enter the value of the relative maximum or a minimum. You won't need to enter the point. You'll just put MAX for maximum and just MIN for minimum in the conclusions column. And anything, if you have more than one situation, like it's increasing and it's concave down, then you need to put a comma in between those. Okay, well, let me get the graphing paper ready so that we can actually graph what we see now. Okay, I'm ready to graph. Now, we have a y-intercept of 0, 0, that's right here. And we have an x-intercept of 0, 0, which is the same point, of course. X and y-intercepts of 0, 0 is both x and y-intercept, it's on the graph. And we have an x-intercept of negative 1, 0, which is right here. And we have a relative maximum at what? What's a relative maximum? Negative 8 over 27, positive 4 over 27. Oh, my goodness. Well, I'm thinking of, you might get a calculator out and put it into decimal form just to make it easier to read. But I tell you what I'm going to do is I'm just thinking this way. 8 over 24 is 1/3, isn't it? So that's a little less than negative 1/3. Okay, so I'm thinking that we're somewhere in this neighborhood, okay, for our x value. That's roughly negative 8 over 27. Now, 4 over 27, let's see, 4 over 24 is 1/6, isn't it? So, you know, it's not a 1/6 here. I'm just kind of giving an idea. It's around 1/6. It's not a very big number, isn't it? Is it? So, you know, I'm thinking that maybe that's roughly about here. So I'm thinking this point is somewhere in this neighborhood. And what is that? That's a relative maximum. So let's remember this. We have a maximum right here. And we have a minimum right here. And remember the little diagram that we kind of drew here? So this is what's happening. Remember, we're increasing from negative infinity to negative 8 over 27, which is where this maximum is. So in this part of the graph, see, we're increasing, aren't we? I made that arrow downward, but we're going left to right, so we're increasing. And then what happens is it decreases from negative 8 over 27 x value, that's right here, remember, to 0. And so now we're on our way down, okay? Well, yes, that's why that's a maximum, isn't it, at that point? And remember that the minimum is, we have at 0, 0, the minimum, so it's going up. And in fact, it's going up, but it's also concave down. And so it's not making it's not holding water up, it's doing this, okay? That's what it's doing. It's kind of the idea that we got before when we put those three parts of the graph together. And of course, that cusp, that point, is why that part of a graph would not have a first derivative defined, would it? And so it kind of fits together with what things we've learned in the past. Well, that's the rough idea of what that graph would look like.